Welcome to a Regents benchmark review. This is for our final benchmark 4 on circuits and waves, the multiple choice part of the review. All right, so our first example here, our diagram below shows a ray of light that is the ray R entering glass from air. So which path is the ray most likely to follow in the glass? I know the answer choices are a little bit out of order here, as they don't correspond with the actual letter that they go with, but we'll try our best to explain this. So whenever you go from one medium into another, there's going to be some bending of light if it is a light ray, and that is called refraction. So that's an idea that you're going to see throughout this unit. So the main idea with this is if the index of refraction is different as well between those two mediums, you will have the bending of light. So for air and glass, on the reference table, there are a few different types of glass, but glass is going to be a greater index of refraction than air. Air is the lowest one at 1.00. So whenever you go from a smaller index of refraction, which is air, into a higher index of refraction, which is glass, it's going to bend towards the normal line. What is the normal line? It is the line that is perpendicular to the surface I'm going into. So this dotted line here is what I'm talking about. That's the normal. It goes all the way down actually along D as well. So when it goes into this new, when the light ray R goes into glass from air, it's going to bend towards this line. So the path that is followed as is ray C here, or the new ray is going to be C. So the answer choice is going to be A because it's ray C. So answer choice A is the answer here. If I was going, say, from glass into air, you would have a difference. It would bend away from the normal. But if you're going from a lower index of refraction into a higher index of refraction, you're always going to bend towards the normal line there in the middle. All right, so example number 2, we have the horn of a moving vehicle produces a sound of constant frequency. Two stationary observers A and C, and the vehicle's driver B, positioned as represented in the diagram below, hear the sound of the horn. Compared to the frequency of the sound of the horn heard by driver B, that is the driver in the middle of the diagram, the frequency heard by observer A is. Alright, so before you even look at any of the answer choices here, a moving object, and when it comes to its frequency, immediately think of Doppler effect. So what is exactly happening within the Doppler effect? What is happening here is when I have a moving object making a sound, it kind of squishes the sound waves at the front of the object and then elongates them towards the end of its movement. So we can make this here. Try to make the sound waves going around. So you can see at the very front, the waves are squished together. Towards the back, they get further apart, so my wavelength actually increases there compared to the front of the moving vehicle where they are much shorter. So we know that in Regents physics, for the most part, we work with sound at STP, which is going to be 331 meters per second, as stated on the front page of the reference table. And we have an equation that relates the speed of a wave to the frequency and the wavelength. That equation is V equals F lambda. So if we have a constant velocity, we must have some kind of, if there's a change in, say, the wavelength here, the frequency must change in the opposite direction in order to combat that. So say at the very front here, going towards observer C, I have a shorter wavelength. So my velocity is the same. So if I have a shorter wavelength here, I must have a higher frequency in order to combat that. It would then be the opposite for A, because I have a longer wavelength, so my wavelength would then go up. So my frequency then must come down. So my answer here is we're looking for observer A. That is going to be lower. There are two answer choices with that. I then go further into the answer choice, and Answer choice A says that frequency heard by observer C is lower. That's not going to be correct because the wavelength is shorter towards observer C, so my frequency should be higher. So answer choice B is going to be my answer for this question. All right, so let's move on to example number 3. All right, so example 3, the diagram below represents a standing wave in a string. All right, so we have here 5 different points, A, B, C, D, and E. What is happening here with a standing wave is moving up and down because it is being reflected off the 2 fixed ends of the wall here. So we have maximum constructive interference occurs at. All right, so constructive interference means that we are essentially building up. So think about very beginning of the unit, we had pulses moving towards each other. If they were on both, say, the top side of the medium, they would move together and create a much bigger pulse. If they were on opposite sides of the medium, say top and bottom, they would cancel each other out. So that constructive interference was the buildup on both sides of the medium. Essentially, in a standing wave, that is what we call the antinode. The antinode versus the node is a place of no displacement. On this standing wave here, we have no displacement at point C. That will pretty much stay in the same place as the wave goes up and down. We will have the same exact thing at point E and point A. So the opposite of that is the wave moving up and down. That is B and D. Again, that is a place of constructive interference. That's kind of like a buildup of the two waves reflecting, or wave reflecting against itself and building up the constructive interference, creating that antinode. So since B and D are the antinodes, and that is where constructive interference happens, answer choice C is going to end up being my answer here. Again, constructive interference, a buildup, getting taller or again bigger, more amplitude in the wave. That is what's happening there at the antinodes versus the nodes at A, C, and E. So let's move on to example number 4. All right, so example number 4, a radio operating at 3 volts in a constant temperature draws a current of 1.8 times 10 to the negative 4th ampere. What is the resistance of the radio circuit? All right, so this is our first math question of this. What I'm going to do with this is see what they give me in the question, match up the stuff on the reference table, and see what equation I'm going to end up using. The first thing that I see here is the radio is operating at 3 volts. Volts goes with potential difference V. That is on the reference table, of course, in the electricity area. So if you look at electricity and forget what voltage is or what potential difference is, you look on the right side, you see that V, that goes with voltage, that is equal to potential difference. So I can put here on the left side over here that V is equal to 3 volts. It says that I'm at a constant temperature. That's more of a conceptual thing. If the temperature is not changing, the resistance is not changing within the circuit over the course of the current being drawn through there. What I have here now is a current of 1.8 times 10 to the negative 4th ampere. So if I forgot that ampere is current, it tells me right beforehand, and I can then look on the reference table and see that current is I on the right side again. So I have here I is equal to 1.8 times 10 to the negative 4th ampere. Finally, I'm being asked to find what is the resistance in the radio circuit. Again, I look at the reference table. If I forget what the variable for resistance is, I see that resistance is big R. So I have here R is equal to what I'm looking for. So that's going to be my question mark. Let me make that better. All right, so I have here my voltage or potential difference, the 3 volts. I have my current 1.8 times 10 to the negative 4th amperes, and I have resistance, what I'm looking for. So I look for an equation that involves all 3 of these variables on the reference table. I can see here that I have an equation R equals V over I. That is Ohm's law. So I'll put here R equals V over I. Now I'm just going to plug in my numbers because everything is done for me algebraically. I don't have to move any of the variables. at all beforehand. So I have here R is equal to my potential difference or voltage, 3 volts, over my current, which is 1.8 times 10 to the negative fourth amperes. All I'm going to do now is plug this into my calculator. Just make sure you're careful when plugging in the scientific notation. So when I plug this in, there's 3 over 1.8 times 10 to the negative fourth. And I should end up with an answer here of 1.6. So it's 16,666. If I do that in scientific notation, it becomes 1.66 times 10 to the fourth, or in this answer choice, so I can put this right here, resistance is 1.7 times 10 to the fourth, and that is in ohms. I have the unit in the answer anyway, so I have answer choice A, 1.7 times 10 to the fourth ohms. All right, so let's move on to my next example. All right, so example number 5, we have here all electromagnetic waves have the same speed in A, flint glass, B, a vacuum, C, alcohol, or D, water. This is just a conceptual question. On the front page of the reference table, you have all the constants. You need to know here mainly that electromagnetic wave is light. On the front page of the reference table, on that constants table, you have that the speed of light in a vacuum is 3 times 10 to the 8th meters per second. So all electromagnetic waves have the same speed in a vacuum is your answer here. So answer choice B is the answer. And that's just based on the reference table. Again, it says there, speed of light in a vacuum. Remember that light is electromagnetic wave. You have in there as well that the EM spectrum shows visible light. Even all the light that we cannot see is counted as light. So your answer here, speed of light in a vacuum, is the same. Answer choice B. So example number 6. Two pulses approach each other in the same medium. The diagram below represents displacement caused by each pulse. Which diagram best represents the resultant displacement of the medium as the pulses pass through each other? So this is going back to the very beginning of our waves unit. You have two pulses moving towards each other in the same medium. This situation, you have one on top and one on the bottom. So very much like going back to either vectors or forces. If you had a force going upwards, it was counted as like positive. If you had a force going downwards, it would be negative. So when you add these two together, you have a positive pulse upwards and you have a negative pulse coming from the bottom. So basically with this, part of it's going to cancel out due to the pulse moving from the bottom there. The square is going to cancel out the like square portion of the shape here. So you have the square here. So essentially this part of the shape is going to end up being canceled out, and you should be left with just the triangle, and that answer choice is answer choice 2. So you just add those together. It's pretty much just that, unless you have some numbers. Same idea. You're either going to have shapes for this, or you're going to have two pulses with some amplitude given to you as a number, and you just add those two numbers together, or depending on if one's on the top or one's on the bottom. That's how you're going to figure out if you're going to add them together, or you're going to have to subtract one of them based on some destructive interference or fully constructive interference. All right, so let's move into our next example. All right, so example number 7, we have the speed of light in glycerol is approximately. So when you get the speed of light in a different material, such as glycerol, you want to use an equation in the reference table that involves an index of refraction and some speed. There are two equations with this, but there is one that is a little bit better than the other. As long as you have what material that you're in and you're trying to get the speed of, it is going to be N equals C over V. The real reason for this equation is that the index of refraction, kind of like the value that is associated with the medium for how light is able, or how fast light is able to move through it, that's essentially the ratio of the speed of light in a vacuum over the speed in that material. So what I have here is glycerol. what I can do is go to my reference table. It's the second page in the Regents table. Under EM spectrum, on there you have the absolute indices of refraction. Again, that's when light is going to bend when it goes into another medium from another one, so air, say, into glycerol here. You go towards the middle of the table and you find that glycerol has an index of refraction of 1.47. So we have here that N is equal to 1.47. Other than that, in that equation, it's N equals C over V. So C is on the reference table on the very first page. That is the speed of light in a vacuum, and that is going to be 3.00 times 10 to the 8th, or just for simplicity, C is 3 times 10 to the 8th meters per second. The last part of this equation is the speed in that medium. That is just V, so we're looking for the velocity in that medium. So V is my question mark. All right, so this equation again writes out as N, the index of refraction, equals the speed of light over the speed in that material, or that medium. Again, the index of refraction, that is essentially the ratio of the speed of light over the speed in that material. The smaller this index of refraction is, the faster I'm going to be going in that material, or the light is going to be going in that material. The bigger it is, the slower the light is going to be going in that material. So what I'm going to do here first is just solve for V algebraically and then plug in my numbers so it goes a little bit quicker. So I have N equals C over V. I want to get V by itself here. So my first step, since it's being divided, is to multiply it on both sides of the equation. So if I do this, I should now have N times V equals the speed of light in a vacuum. And then finally, to do my last part here, to get V by itself, is being multiplied to the index of refraction. So the opposite of that would be then dividing out the index of refraction from both sides in order to get my velocity V by itself. So my speed of light in this new medium is equal to the speed of light in a vacuum, C, over the index of refraction. So we should now just be able to plug everything in and get straight to the answer, because it's now my velocity equals speed of light over index of refraction. So velocity is V. C is 3 times 10 to the 8th meters per second. This is over my index of refraction, which is 1.47. All right, so plug this into your calculator and you should get the answer that is fairly close to one of these answer choices. So 3 times 10 to the 8th divided by 1.47. That's going to give me an answer there of, let's see here. So I have 204,081,632. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be 2 times 10 to the 8th, because I have 9 numerals before my decimal. So 2.0 times 10 to the 8th meters per second should be my answer here, and that's what you end up with in the calculator. If you're not so sure about that, you can do the scientific function on your calculator. You can change it into that mode and it will make it in scientific notation for you. Or if you have a really big number like that, all you do is count all the numerals before the decimal and then minus 1. That's your scientific notation. So 2.0 times 10 to the 8th meters per second is going to be my answer here. All right, so let's move into our next example. All right, so we have a singer demonstrated that she can shatter a crystal glass by saying a note with a wavelength of 0.320 meter in air at STP. What was the natural frequency of the glass? All right, so there's a lot of stuff going on here. The phenomena that this goes with is resonance. When we have a natural frequency, when we do the same exact frequency as the natural frequency near that object, we can get that object to then vibrate. That's not as important here as actually doing the math now. So what we have here in the question, the first thing I see here is a wavelength of 0.320 meters. If I look on the reference table, what is wavelength? Wavelength is lambda. So I put in here wavelength is going to be equal to 0.3, let me make that a little bit nicer. So 0.32 meters. What I also have here is in air at STP. I'm going to come back to that in a second because that's going to be important, but I'm going to move on for one moment and see here that I'm being asked to find what is the natural frequency of the glass. So essentially, what is the frequency here? So that is my question mark. And the last thing here, I don't have enough right now to find the frequency. But what I do have here is that I'm singing a note in air at STP. So singing is a type of sound. So we should be able to see that on the reference table, we have sound at STP in air. And that is on the front page as well in the table of constants, or list of physical constants. Below the speed of light in a vacuum, you have there 3.31 times 10 to the second meters per second, or in better terms, 331 meters per second. That is the speed of sound in air. So that's what they're giving us when they say in air at STP, and you're singing that note. So the velocity here of the wave is 331 meters per second. So there's an equation that involves velocity, frequency, and wavelength. It is the first one on waves. So we have there v equals f lambda. So now we can write this all out. V equals f lambda. I'm looking for my frequency. So again, I'll just do the algebra beforehand here so we can do the math plug-in in one step. So I want to get frequency by itself. It's being multiplied by my wavelength. I can divide this out from both sides, and I end up with velocity over wavelength equals my frequency. So I can just plug this into the equation and I can get the frequency straight away. So I have here 0.3, let me fix that again. 0. Ooh, that's not the correct one, that's the velocity. So I gotta put here velocity on top. That is supposed to be 331 meters per second. That is over my wavelength, which is 0.32 meters, which is then equal to the frequency. So now plugging this into my calculator here, I have 331 divided by 0.32. My frequency is then going to be 1034.4 hertz. So 1034.4 hertz is equal to my frequency. Again, we have it here in scientific notation. So the best way to go with this, I should have here, I have 4 numerals before my decimal. That is going to be 10 to the third. There's only one of these with 10 to the third, and it lines up with my answer here. So 1.03 times 10 to the third hertz equals my frequency here, and that is answer choice C. So let's move into our next example. All right, so example number 9 here, you have a transverse wave is moving toward the right in a uniform medium. Point X represents a particle of that uniform medium, which diagram represents the direction of the motion of particle X at the instant shown. All right, so this seems to be one of the more difficult questions that comes along, even though it's not like one of the really hard math questions that you see. Sometimes it's a difficult concept to grasp as we go through the waves unit. So with a transverse wave, the particles are always going to be moving up or down. So essentially 1 and 2 can go away right away because that would be the movement in a longitudinal wave, and this is not a longitudinal wave. Longitudinal wave moves side to side. So 1 and 2 can go away right away. Now is where it becomes a little bit tricky. So essentially, particle X is going to just ride the wave as if you were like on a roller coaster, but like a roller coaster where it's a conveyor belt moving like forward and you're staying in the same place the entire time. So the direction of the wave motion is important here as it is moving to the right. So that is going to dictate whether our particle X is going to move up or going to move down. So if it's going to ride the wave, it's going to go as the wave moves to the right, the upper crest is going to move where the particle X is now. So the particle X is going to ride that wave and move on the crest and go upwards. It is not going to go down. So you should have answer choice 3 here, as the particle X is going to move up. That is all done by the direction of the wave motion. If it was going in the opposite direction, then you would have answer choice 4 as it would have to go down as that's how the wave is moving. But essentially you're on this like conveyor belt or like a wave. Have you ever seen like in the ocean they have like the bridges that are like wave bridges that kind of like move with it? If you stay in the same place and the wave was coming towards you and that wave was in a crest, you would go up with that. So that's essentially what's happening there. The wave is moving towards the particle X, and the particle X just goes where with the wave is moving, so it's going to go up in that situation. Answer choice 3 is my answer. All right, so number 10. Which particle would produce a magnetic field? This goes back to a lab that we did a little while ago. It was a little bit of an odd simulation. It showed this particle that was in this magnetic field, and you had a slider in which you could increase the velocity at some percentage of the speed of light. So you have to have something that is moving. So we have here 3 answer choices that involve movement. So you can get rid of the one answer choice that is not involved in movement, which is answer choice C. The other thing that we had in that simulation was that the particle was charged. So answer choice D is going to be your answer here. This is more of just a memorization thing, at least for our purposes. Because we don't get too much deeper into magnetism besides this and the magnetic field lines. So you just have to pretty much memorize that a moving charged particle is going to create a magnetic field, and that's going all the way back to a lab that we did with that with a simulation. As you increase the speed, you had a stronger magnetic field, and you decrease the speed, the magnetic field was lessened. So what we have here is a moving charged particle. Answer choice D is my answer. All right, so moving on to the next example. Number 11. Which diagram best represents wave refraction? All right, so we've talked about refraction at least a few times here over the course of these questions. Refraction is the bending of light or wave as it moves from one medium to the other. So let's just look at all these answer choices and see what's happening in all of them. All right, so the first answer choice, we have an incident light ray goes onto, let's say, a mirror and it bounces off. This is going to be reflection, not refraction. So answer choice A is going to go away right away. At answer choice B, we have our wavelets moving towards a open slit. And as this happens, the wave then bends. This is called diffraction. We just learned about this the other day. This is not moving from one medium to the other, but just moving through an opening or some kind of like closed off area in a medium, in the current medium that's in, and that makes the waves bend to get through that opening or around that barrier. So that is not correct either. Answer choice C is the same situation as another example of diffraction. As it goes around the barrier, the wave then kind of like splits and bends around it. So that is not going to be right either. And answer choice D, then by process of elimination, is my answer. And also, I have here the wave is going into the new medium, is bending towards the normal line as we go from one medium to the other. That is called refraction. The bending of light from one medium into another medium. So that is my answer here. Answer choice D. Let's move on to our next example. All right, so number 12. We have here, if the amplitude of a sound wave is increased, there's an increase in the sound's what? All right, so amplitude essentially has to do with the height of a sound wave, or how much energy a sound wave has. All the other stuff here that we have loudness, we have pitch, we have velocity, and we have wavelength. Pitch has to do with frequency. That is essentially analogous to frequency, or the same as frequency when we are dealing with waves. The only thing that is going to change frequency is a change in the wavelength. So that is not going to happen when you have a change in amplitude. Velocity, the only thing that's going to change velocity for sound is if the temperature is changing. If amplitude increases, that is not the case. So those two are gone at the moment. Wavelength, the only thing that is going to change wavelength, besides the temperature change, which is might change the velocity. The only thing that's going to change wavelength is a change in the frequency. So that's not happening here, or if the wavelength changes in any capacity, it doesn't say that the wavelength is changing. A change in amplitude does not change the wavelength of the wave, so that's not going to be correct either. So our process of elimination, it's going to be loudness, and that just has, and just by the idea behind it as well, or the concept, amplitude, the greater the amplitude, the higher the loudness is, or the more energy the sound wave is carrying, so the louder it becomes, the more decibels you hear, things like that. So loudness is going to be my answer here. That is the same thing as amplitude. For our increase in amplitude means an increase in the loudness of the sound in our situation, or just in general. Example number 13, we have here, which change decreases the resistance of a piece of copper wire? All right, so our answer choices here are going to kind of drive how we're going to do this question. So we have here A, increasing the wire's length, B, increasing the wire's resistivity, C, decreasing the wire's temperature, or D, decreasing the wire's diameter. All right, so length and resistivity. So let's run out what these things are. So length on the reference table, when you're dealing with copper, you're dealing with resistance. You're going to be in the electricity portion of the reference table. So you're going to go there and look for what these variables are. So I see here length first, so that is going to be L. I also have in the second answer choice resistivity. Resistivity is the Greek letter rho. It looks like a P. So we have here rho. Let me fix that. We have there the wire's temperature. There is nothing about temperature on the reference table besides the resistivities at 20 degrees Celsius. Alright, D, decrease in the wire's diameter. Diameter can deal directly with area, and area is on the reference table there. A, cross-sectional area, so A is here. And we're trying to decrease the resistance, so R. So what equation deals with resistance, resistivity, length, and area is going to be R equals rho, or resistivity times the length over the area, or cross-sectional area of the wire. All right, so let's see what happens to the resistance if I do what they're telling me to do here in my answer choices. So increasing the wire's length. If I did that, that is a direct relationship since it is on top here. If I increase the wire's length, I would then also increase the resistance. I want to decrease the resistance, so answer choice A is incorrect. So B, so we'll write this out again. Increasing the wire's resistivity, that is also on top of the equation. So if I increase the resistivity, I would also increase the resistance. It's a direct relationship. So that's going to be the incorrect answer. Temperature is not in the equation, so we'll come back to that one in a second. D, decreasing the wire's diameter. That is going to then decrease my area, so writing out the equation one more time. Rho times L over area. If I decrease the area, is a indirect relationship or an inverse relationship in this situation. So if the bottom goes down, resistance then will go up as well. So that is also incorrect. So by process of elimination, C is going to be your answer, but also decreasing the wire's temperature decreases the resistivity. And resistivity, as we saw, is a direct relationship on the top of the equation. So if I decrease the resistivity, that is also going to decrease my resistance. That's why on the reference table, it says resistivities at 20 degrees Celsius. That tells you that the resistivity, or it's going to say in like a question, that a wire at 20 degrees Celsius, that's telling you that the temperature is not going to end up changing. So that resistivity is then valid. So if I decrease the temperature, the resistivity value will actually also decrease. And since it is a direct relationship, it will decrease the resistance of the wire. So answer choice C is going to be my answer. All right, so let's move to example number 14. All right, so the diagram below shows waves A and B in the same medium. So B is going to be the solid line, A is the dotted line. Compared to wave A, wave B has. So look at wave B versus wave A. That means, so look at this, just based on what I'm looking at right now, wave B is a taller wave. So that means it is going to be have more amplitude. So if I look at any of these answer choices, I'm looking for one that says either twice the amplitude or whatever is going to be more amplitude. A says twice the amplitude, B says twice the amplitude, C and D do not have that. C says the same amplitude, and D says half the amplitude. As I can see here, B is much taller than A, so it's going to have a greater amplitude, so C and D can go away right away. So I'm left with A and B. So A says twice the amplitude and then twice the wavelength. Wavelength here, when I don't have really a measurement, what I can do is look at the cycles of both waves and the distance that I have here and then figure out which one's going to have a greater wavelength. Essentially, more cycles over this distance means less wavelength. So if I look at B here, the cycle is going to start at this point. It then has to go up once, come back to the middle, go back down, and come back to the middle. So that is one cycle. The second cycle I'll do in green here. So that's the beginning of the cycle, goes to a crest, comes back to the equilibrium position, goes to a trough, comes back to the equilibrium position. That's two cycles. And then I'll do the last one here in blue. The beginning of the cycle at the equilibrium position, the next part of it at the crest, come back to the equilibrium position, go down to now the trough, come back to the equilibrium position. So B has three cycles, whereas then A, so I guess I could do orange for A starting at the same point, I go up once, that is my crest, come back to the equilibrium position, go down to a trough, come back to the equilibrium position. That's one cycle, and then I really only have a half a cycle left. I don't have to go through that again. So you can see that B has many more cycles than A within this diagram. So the more cycles within this length means that I'm going to have a shorter wavelength. So it can't be answer choice A. So by process of elimination, it's going to be answer choice B. So we have twice the amplitude and half the wavelength. That makes sense because I have 3 cycles for B, I have 1.5 cycles for A. So that's going to mean I have half the wavelength here for B. So answer choice B is my answer, twice the amplitude and half the wavelength. Let's move on to example number 15. All right, so example number 15. As a longitudinal wave moves to a medium, the particles of the medium. So we have here a few answer choices. We have vibrate parallel to the direction of the wave's propagation, vibrate perpendicular to the direction of the wave's propagation, are transferred in the direction of the wave's motion only, and are stationary. I can look at one of the answer choices here and get rid of them right away, and it is answer choice D. These are not stationary particles, so that's gone right away. Of the other answer choices, answer choice B, vibrate perpendicular to the direction of the wave's propagation. That is going to be a transverse wave. We pretty much did that one already in an earlier example, so that one is not going to be correct here. And we're looking at answer choice A and C. And the best one between these is going to be answer choice A, vibrate parallel to the direction of the wave's propagation. Essentially, think about the slinky. As the slinky gets the compressions pushed down it, you kind of saw the parts of the slinky, like the compressions moving down. That's moving parallel to the direction of the wave's propagation. Propagation just means like the movement of the wave, essentially. So it's vibrating back and forth or parallel to the direction of that movement. So answer choice A is going to be your answer here. For longitudinal waves, again, that's a sound wave. If you have a transverse wave, that's when you have it as perpendicular. But a longitudinal wave, think long, is a long wave. It is going to be your sound wave. It vibrates the air molecules back and forth for you to be able to hear the sound in your ear. So answer choice A, vibrate parallel to the direction of the wave's propagation, is going to be your answer. All right, so example number 16. We have a 3.5 meter length of wire with a cross-sectional area of 3.14 times 10 to the negative 6 meters squared is at 20 degrees Celsius. The current in the wire is 24 amperes when connected to a 1.5 volt source of potential difference. Calculate the resistivity of the wire. All right, so we have a lot of information here. What I'm going to do again with a math question is write out everything that I have in the question, what they've given to me, use those variables, then find an equation on the reference table. All right, so the first thing that I have here is a length. So 3.5 meter length. I can see on the electricity portion of the reference table, length is L. So length L is 3.5 meters. What I also have here next is a cross-sectional area of 3.14 times 10 to the negative 6 meters squared. Cross-sectional area is also on the reference table there at the very top of electricity. It is A. So I have here that A is equal to 3.14 times 10 to the negative 6 meters squared. Next thing is that this is at 20 degrees Celsius. That means that the resistivities on the reference table would hold valid, but we're not using one of the reference tables, so that's not really going to matter for the most part. It's just also tell us that we have a constant temperature. So the resistance is going to be constant. The current in the wire is 24 amperes. So that is going to be on the reference table, that is I. So again, that is on the right side. So I is equal to 24 amperes. This is then connected to a 1.5 volt source of potential difference. A source of potential difference that is going to be V on the right side of the reference table, essentially a battery. So V is equal to 1.5 volts. And I think that's all I have at this moment. I'm trying to calculate the resistivity of the wire, so I do not have that. I'm looking for that. That is a question mark. But an equation that involves a resistivity, area, and length also involves a very important variable. If you're looking at that equation on the reference table, it is R equals rho times L over A. I also do not have my resistance. So I have to also look for resistance R here. So I'm going to do that first because otherwise I would have two missing variables in the equation. R equals rho times L over A, and that's not going to work in this situation. So I need to find my resistance first. I do have enough here in order to find that resistance. In the things that I wrote down, I have my voltage and potential difference. So if I look at the reference table on the left side, R equals V over I is the equation I'm looking for. I'm looking for Ohm's law. So R equals V over I. Now I can just plug in the numbers that I have here. My voltage is 1.5 volts, or my potential difference is 1.5 volts. My current is 24 amperes. So I'm just going to plug this into my calculator, and I'm going to end up with my resistance. So 1.5 divided by 24, that is 0.0625 or 0.063. So my resistance here is 0.063, and that's ohms. So now I have my resistance. Alright, so now I'm only missing one thing from the equation. Resistance equals resistivity times length over area. Since we're dealing with a lot of, or we're dealing with a number that has scientific notation, it's easier to solve for rho first, get on one side of the equation by itself, that is to plug in the numbers and then deal with it that way. So I'm going to take my equation here. R equals, so I'll write it out one more time, R equals rho times L over A, and I want to get rho by itself. So my first step towards doing that is being divided by the area. So if I multiply the area on both sides, that is the opposite operation. I will have resistance times area equals rho times L. And it's already looking a little bit nicer. I want to get rho by itself is being currently multiplied to the length of the wire. I do the opposite of that, and I divide out the length from both sides. So I should end up with my resistance times the cross-sectional area over the length equals my resistivity rho, and that should just make our life a little bit easier when plugging in our numbers now. Alright, so the first thing I'm going to plug in here is my resistance. So that is 0.063 ohms. I'll make that look a little bit nicer. So 0.063 ohms there. That is times the cross-sectional area, which is going to be 3.14 times 10 to the negative 6th meters squared, all over my length, which is 3.5 meters. That is equal to resistivity rho. The first thing I'm going to do here is multiply the two top numbers together. So 0.063 times 3.14 times 10 to the negative 6th. That's going to give me on top here 1.98 times 10 to the negative 7th. And that is ohms times meters squared. Over 3.5 meters is equal to resistivity. So then I'm just going to divide these two numbers. 1.98 times 10 to the negative 7th over 3.5. So 1.98 times 10 to the negative 7th. Divide that by 3.5 in your calculator, and you should end up here with an answer of 5.66. So it's a little bit off due to our rounding, but it's the closest one is 5.61. So 5.66 times 10 to the negative 8th. 5.66 times 10 to the negative 8th here. Let me fix that. And that is ohms times meters in this situation, and that is equal to rho. Since we rounded off a little bit for the resistance and actually for the top of the equation there when we were solving for rho, it's going to be a little bit off from the actual answer choice, but it's going to be closest to 5.61 times 10 to the negative 8th ohms times meters. So answer choice A is going to be your answer. Alright, so let's move on to our last two examples. Alright, so example number 17. The diagram below represents a light ray being reflected from a plane mirror. The angle between the incident ray and the reflected ray is 70 degrees. So the main thing you need to go from, or the concept you have to go from for this question, is the law of reflection. That's on the reference table as theta I is equal to theta R. That means that the incidence angle, or the angle of the incident ray, is equal to the angle of the reflected ray with respect to the normal. So the normal for this situation should just be straight up and down. It is perpendicular to the plane mirror, so it would be like this up the middle. So essentially, you're just going to cut 70 in half because the angle over here, so there's one in red, so the angle here is going to be equal to the angle over here. So just cut 70 in half, and you're going to end up with the angle of incidence being 35 degrees, because the angle of incidence is going to equal the angle of reflection. Let's move into our final example. All right, so our final example. In a vacuum, a monochromatic beam of light has a frequency of 6.3 times 10 to the 14th hertz. What color is the light? All right, so we have here a bunch of the visible light spectrum. If you're wondering why you just have on your worksheet for the class that you have here no value before the hertz, it was just a misstep when I was getting the questions into the worksheet. I guess the number was seen as a picture instead of letters, so it didn't copy over. This is a number that you should have. It should be 6.3 times 10 to the 14th hertz. So there's two versions of these type of questions. The one that's a little bit harder is you might be given the wavelength of light, and then you would have to calculate for the frequency. But lucky for you in this situation, you're given the frequency of the light. That is relevant because on the electromagnetic spectrum, this is where you would go here, the second page of the reference table, you are given all the frequencies, or the range of frequencies, for the visible light spectrum. So what you're going to do with this is just take this number and then line it up in between two of the numbers on the visible light spectrum. So if I look at the very beginning of the visible light spectrum, I start at 3.84. They're all times 10 to the 14th, so that's not really going to matter here. So just looking at the first number here. So I start at 3.84 and go to 4.82, and that is red. Obviously 6.3 is bigger than that, so we move over. 4.82 to 5.03, that is orange. Again, 6.3 is bigger than that, so we continue. Yellow is 5.03 to 5.2. We're getting closer, but that is still doesn't fall in that range. 6.3 is bigger than those two numbers. We keep going. Green is the range of 5.2 times 10 to the 14th to 6.1 times 10 to the 14th. We get a little bit closer, but not quite there. Finally, we get the blue, which starts at 6.1 times 10 to the 14th and goes all the way to 6.59 times 10 to the 14th. 6.3 would be right in there, so it falls within that range. So we should have a blue light in this for this frequency. So the answer choice here is answer choice C, blue. All right, so I hope these examples were helpful, and this will help you and study for your benchmark. Good luck, and see you all in class.